Right, so apparently in JC's talk, there was some glitch with the YouTube streaming and the YouTube recording was truncated, but hopefully the cloud recording is okay and we will replace it, and hopefully it's just a one-time occurrence. And yes, of course, for people who are here, it doesn't matter that much unless they want to go and watch again after that. But if anyone here does want to go and watch, then the last 20 minutes are missing until we replace them. So I guess we can wait another minute or so before we start.
Okay, so you should be able to share from your tablet now.
Okay, I will do this shortly. Okay, to adjust the thickness. Good. Okay, I don't know if I should start or I'm still wait.
Yeah, okay, I think it's a good time to start. So yeah, so welcome everyone to the second talk by Kavita Ramanan. And please.
Okay, so first let me start by asking if people have questions. And again, I'd like to very much encourage people to just unmute and ask questions as we go along. If not, is there anybody here who wasn't there on the first day and needs me to write down again what was the basic dynamical system that we were considering? If so, I can do this just after I write the theorem. So please just unmute and ask yourself. Otherwise, we're looking at these locally interacting stochastic processes, which are Markov chains or diffusions. I mean, I will write down these equations as we go along as well, but I just wanted to remind you, we're trying to understand the asymptotics. And the first thing we did was we came to the first theorem, which said that if the graphs and along with marked with the initial conditions converge in the local sense to a limiting graph along with its initial condition, then that implies that the whole process, that is the graph marked with the process, which we denoted by X, which depends on of course, the graph structure and the initial condition, and this is the whole process, converges to the limiting graph, the dynamics on the limiting graph. And so this is marked with path space, right? That was what we said. Okay, and so what is the basic idea that we want to show? So let's just look at how you might prove this. And so idea of the proof. And I have written this in the form of the Markov chain, and we will be writing the Markov chain dynamics. So let me just remind you. So in the Markov chain case, it's quite simple. So this is not a very surprising result, this local weak convergence. It's just the first step. And I said as our main goal is to understand the third step. And I would actually like to repeat, because I said this at the very end in the last lecture, that a similar local weak convergence result for another class of diffusions, which I've put on the slides, which I'll post today, was also independently obtained by Guillermo and Rice. They looked at certain, in some senses more general, in some senses more restrictive class of diffusions. Okay, so let me first tell you what happens in the Markov chain case. And so we said, so the Markov chain case, remember that the dynamics is just, and I'm writing this really in the Markov chain because we could do it for, of course, non-Markov dynamics as well. So we have that the dynamics of the V particle at times k plus 1 is some nice continuous function of the state at time k, and then all its neighboring states at time k. And of course, some external noise, which is independent across vertices. Okay, and time as well. So this would be actually k plus 1. So, okay. Okay. So in this case, that the idea of the proof in the Markov chain case is quite simple. It's just an inductive argument. And that's really not hard to see at all. So I can do it in like 2 lines. So you can easily see that if you look at, of course, you know that the graph marked, I mean, I'll just write. So if you look at, of course, xv0, x0, gn. And so I'm leaving out this, but this is all there here. Okay, so if you look at x and z0, of course, that's going to go to x g0 by assumption, right? That's just the assumption that the initial conditions converge in the right way. So I don't think I really need to write this out in great detail, but it's pretty clear that now I need to prove we can only, though we're looking at the entire trajectory, it's enough to look at sort of finite lengths. So we only need to prove that this gn, xgn, say for any k, I'll use this notation, converges. And I'm going to leave out the initial condition in the superscript for notational convenience. So we have this for every k, where this square bracket here is always going to represent the whole history of the process, which is going to be x of, x at time 1 all the way up to x at time k, right? So even though you want to look at the entire path, it's enough to look at any finite path segment. Okay, so just like, when you want to look at trajectories, it's enough to look on compact intervals. Okay, and so, but then this is really clear that if you know that this, if star holds, then you just simply need to show, you can notice that then, of course, x v k plus 1 can be written as a continuous function of all the other of xvk and some random noise. So the past, that's just the dynamics are really, really simple, right? And some independent external noise. Is that clear? For every k plus 1, is everyone clear about this? I'm just using this fact, this dynamics, okay? Because xv at time k plus 1 depends on f is continuous and it's some, so for phi, some continuous function from chi k cross the noise. And sorry, it's not depends only on just nu, sorry, this is wrong. It depends on a neighborhood of, so some finite neighborhood. Right, of course, it depends on the past also of the U neighborhoods. And each time you do a step, it will depend on sort of more and more of the past, but it won't depend on more than a k level neighborhood of this. Do you understand? So The first time, it's just that there's this triangle dependence. So suppose we have a Markov chain. Let's see what the dependence is. And so here at time 0, you have all these values. So k equals 0. Then at k equals 1, this vertex, these are all the vertices. So what about this will depend, it will depend on the values that were here and here, right? The next step, it will of course depend on these values, which in turn would have depend on these. And one more step, you have the same thing. This will depend on these and this and this. So you have this sort of cone dependence, conical dependence on the past. But the point is that any finite neighborhood at any time k will only depend on a finite neighborhood at time 0, a much larger finite neighborhood at time 0. Right? And so that's very important because local weak convergence tells you only that finite neighborhoods converge, right? For any given finite. So I know that all the values here, by assumption, the initial condition, the finite neighborhood converges, but this is some nice continuous function of all those values in this red here. And so for any finite neighborhood at time k as well, its values are going to only depend continuously on the original one and that. So that's sort of proof by pictures, right? Which tells me that, so because of this conical dependence, so you can prove by convergence easily. Okay, any questions? Okay, so that's very simple. But now let's look at diffusion case, where we obviously know that the same argument cannot hold, right? Because we know that so let me remind you what the dynamics for the diffusion case is. And now I'm just, okay, I'll Gn xn. So yes, so there was a question in the chat that, is it clear that psi is continuous as a function of the graph? Yeah, I mean, psi, remember, it can be given explicitly in terms of recursive definitions of f and just the values at 0. So really, I could have written this more explicitly, but xv of k plus 1 will be f of xv gk and k, and then each of the xu's can be written as f of the previous values and some just random noise. And all these random noises are independent, so it will be continuous. So you need to do that small check. Yeah. And anyway, we have a deterministic graph right now. And then because we said the random graph case will just go immediately. So it only depends on a neighborhood. Okay. Okay, great. Thank you for the question. So now we'll go to the diffusion case. So remind you, again, I'm going to keep this simple for notational setting. I'm going to just write this as, I'm going to make the diffusion coefficient this is a neighborhood, and then dt plus dvt, right? So this is for any graph. Let me just write this, xg, and I'm leaving out, again, the initial conditions for simplicity for now. And I may put them whenever I need to emphasize, but otherwise I don't need to. Okay? So everybody clear that this was the dynamics where B was nice and Lipschitz continuous and everything. So now what might we do? And of course, this is important to write because we're interested in what happens when you have some initial conditions, right? Of course, so suppose I just looked at another process on the same graph with the different initial conditions, then which are then converging to that. One knows this is standard SDE. You can show using Picard iteration, Lipschitz continuity, that of course the things will converge, right? So that's an obvious observation that if you had if you had some x tilde GV with the same dynamics, but with a different initial condition, So, so this would actually depend on n, because only it's the same graph, but it depends on n because I'm going to change the initial conditions, right? So to some values. So with different initial conditions that converge then standard methods show that, okay, this has nothing to do with local weak convergence. This is a stochastic analysis and just Doobb's inequality, just Picard iteration type methods. Then standard methods show that x tilde Gn would converge to xg. Okay, but now we don't quite have that. We know that Gn itself is different. So if Gn were actually a subset of the original graph, and so it was exactly isomorphic, then we would do something also quite similar, right? And if the xv's were close to the xnv's, then for every v in this graph, then again, you could use the same Picard iteration. Is this clear? But we're not saying that we have this other graph Gn and it's isomorphic. So what we will try to do in the diffusion setting, so it's a bit more complicated. So first I will just outline the steps. Okay, so I will outline the steps, main steps. So main steps. Okay, first we just make the trivial observation again that suffices to look at finite time intervals to show for every t in finite t that you want to show that this and this is again the past of xgn up to time t. Okay, this converges in law to g x g x t, right? Okay, so that's so should be cap t. Okay, so we know that. So, but now we only know that there's some isomorphism. So if we knew that x and v, what I was trying to say that if Gn was actually a subgraph, and we would know that xnv converges to xv, then easy. But we don't know that, right? So instead, what we want to do is we want to couple the dynamics of the xgn and xg and sort of put it as if it were sort of the same graph. So what would you do? So we first fix epsilon greater than 0, and then I pick some L neighborhood, because when I do want to do local weak convergence, I just want to show in a L neighborhood of the root, these two dynamics are close, right? And I fix an epsilon, and then I fix some large k, which I will choose later, but the k is going to be larger than L. I can choose it later. And then I will choose an n, which of course could depend on k, such that for all n greater than k, I have my initial condition. So there exists some isomorphism. So the reason I'm doing this proof is because this is I'm doing this proof is so that you sort of see how this, when you want to do local weak convergence, how these sort of isomorphisms come in a sort of simple setup. So I know that there's an isomorphism that will go from bk plus 1g to bk plus 1, that is a k plus 1 neighborhood of g to a k plus 1 neighborhood of gn, such that the initial conditions in that neighborhood are controlled by this epsilon. say some squared is less than some epsilon by 3. I mean, this is just small enough. Yes? Okay. But now I have this little, I have a G here, this graph, and I have a V here. And then, of course, I have a Gn, which is outside. Somewhere it's another graph. And I have a phi n of V. Yes, for all n then greater than nk. Thank you. Indeed, greater than large n. And then I have this isomorphism phi n. Okay, and this may have some neighborhood. And then this would also have some neighborhood. And we know that the neighborhoods are mapped to neighborhoods because this is an isomorphism. Okay, so we want to estimate the distance. So we want to estimate the distance between the laws of xv gx for v in this neighborhood, actually the L neighborhood of the root, and x and of course the xv gn xn. Okay, say, and for now I'll just say in this G, but we are really interested in the distance in the sense of local wave convergence, so we're interested in balls. So it's always hard to estimate laws. So what do? You try to couple them and put them on the same probability space. So remember that the dxvt has this dynamics, okay, this dynamics, which is driven by some Brownian motions W. So what I'm going to do is I'm going to define some other, I can always extend the probability space, define some other Brownian motions, and try to find another process on that space, which also are driven by this WV, but have the same law as my XVGN. So how can you do that? Well, you want the WVs to look like, so I will define some new Brownian motions. So suppose I have another sequence, so couple the process. Aim to couple the processes. I won't give all the details, but to give you some idea. Okay, so you can say, suppose you have an infinite sequence of Brownian motions, V in Gn and for all n and n, all IID Brownian motions. And then I'm going to have this new process driven by these WVNs, which is going to be equal to, so remember I'm here, so if I go back, I will want the Brownian motion on Gn to be the Brownian motion that is phi inverse, like phi n inverse of V, okay? So that the Brownian motion corresponding to the vertex phi n V will be the same in Gn as the Brownian motion that was corresponding to V, because that's the isomorphism. So this will be only for V in this neighborhood. And then I define this just some other arbitrary Brownian motion in the remaining. Okay, and then it's a little exercise. You can define, I mean, this is trivial to see that then if I define xvnt to just be b xvnt, x, again, the neighborhood of Gn, n of t dt, plus dwvn of t, with my initial conditions x0, right? So if I define this, then this clearly has the same law. So this has the same law as my xgn xn, right? Because I can always change my Brownian motions, it's still all IID. Okay, because it's an isomorphism, I've taken 1-to-1, so all these WVNs are just some IID Brownian motions. You have a strong solution. This is the same in law. I haven't really changed the dynamics at all. Is this clear? Okay, but now I want to put both of them sort of looking like in G. So then if I define instead, I really want to transform this so that I'm driving this WVN by sort of, remember that WVN is actually W phi n inverse V. So I'm going to now define a YN, which is equal to X of phi n of V. The whole point of this is then W of N of phi n inverse is going to be exactly WVN by definition, right? Okay, so now I have another WY. I can define this process WVN to, of course, be, what is this? So I'm just replacing V by phi V in this, right? I replace V by phi V in this equation 2. And we'll call this original equation 1. And so now if I replace this, by phi V, of course, this will again give me WNT. And now because phi n is an isomorphism, it's not hard to see that this will actually, you can say that this is still the neighborhood of V of Vn, because neighborhoods are preserved by isomorphisms. Because what this would actually be is X phi n U in a neighborhood of V, but that's the same as YV, V in a U in a neighborhood of V. So that's easy to see. And then now plus this will be dW of, phi n, but that's just going to be my WVN. So then, so now I get my WV. Okay. Right? Because here, if I put my phi V here, then I plug that in here. Phi inverse of phi is just V, and that's just W. Okay, so it's a little bit of a coupling. You don't have to have followed all the details. But if you have that, then you can easily now compare. And of course, YVN now, 0 is exactly X phi n V. Okay, so anyway, you did some sort of Brownian motion manipulations, and now I get another process that's driven by the same Brownian motions and with the initial conditions that are closed. So now we can compare Yn and X by standard methods, somewhat standard methods, just the usual Picard iteration, to show that if we define this difference, delta Vn, to just be the usual L2 distance of the supremum, which I will denote by a star. Sorry, maybe I'm not moving the screen up. Okay, at time t. So the star just means I'm taking the supremum of the entire trajectory up to time t. So this is for all t in this big cap T. Then you can just use sort of usual, yes, YNV is just defined through the BVNs for that. I didn't write that. So someone asked, how is YVN defined outside that? It's just driven by the usual, YVN is just equal to XVN. It's all driven by the Brownian motion. So that's, you don't have to change the definition of YVN outside. This is only for V inside. So I'll of course put notes with all these details. I'm just trying to give you a sense in this during this. And it's equal to XVN outside. I don't have to do any transformation. Okay. So so now you have this. You can do usual standard inequalities. Will tell you that you use for standard that delta VNT is equal to less than or equal to some 3 times this difference of the initial condition, which is why we showed some epsilon over 3, plus some, sort of Gronwall ready term. And where is this coming from? This is coming from the Lipschitz continuity of the drift, which has 2 terms, right? One is with the state term, which just gives me this delta NBS, and another is the neighborhood term. And that Lipschitz continuity gives me this sort of empirical measure type difference. Okay. And now you think, okay, I'm almost done. Well, okay, this is going to be less than epsilon plus some C1, which is integral 0 to t. The max of all of these are going to be within a radius 1, right, of V. And I look at the max difference in that case. Okay, so you might think, okay, now I'm done. I just apply Gronwall and I'm done, but it's not, because the problem is that this is, you don't usually for a Gronwall, you need something that is decaying here, right? You need something that's decaying here. Here you just have some constant, and all you know about this is uniformly bounded, and that comes from the fact that you're assuming that the initial conditions are bounded uniformly in some ball of R, okay? So we assume that. Remember, that's where this condition comes in. So, okay, unfortunately, so what you have to do is, in fact, there's a little more work than the standard Picard iteration. Now you can apply the same estimate to delta U. So you can reiterate by applying the same estimate to the vertex U, right? And you can keep doing that up to, of course, you cannot do it more than n, but n is something that's growing large. So, and you can't, and it's, so I can choose some large M and keep iterating. So choose, so iterate many times. To get a, so sort of I can choose M to be something that is, so K is large, and I'm going to let M be L, K minus L. So iterate M many times. I cannot do it more than L, right? Because I want to get to the boundary of this ball, BK ball. And so then I can say that you can show that this is going to be less than or equal to. So each time you iterate, you will get a term just in the usual Gronwall, usual iterated Picard iteration, where you'll get a term that depends on M. Okay. So the details of which you do not have to absorb fully, but the idea is that now you have this ball. So remember that we're doing something similar to the Markov chain case, which is for the Markov chain case, in the initial conditions, you had control over a smaller, you have to have control over a much larger ball. If I want to understand what is happening in a L neighborhood of my, at time K, I have to look at sort of a much larger, or almost a 2L plus 1 or something neighborhood at 0. So here too, we're doing something, except it's not like L to 2L plus 1, and it's not exact, but we want to look at an L neighborhood of the whole trajectories up to this. And we have to sort of do this iteration and enlarge what's happening to get a sort of M neighborhood of the initial conditions. And now you have this, so now this M is K minus L, right? So I could have just written this as K minus L, in fact. So there's no need to introduce this M. But the point is I do M iterations, iterate M times. So M equals K minus L times, and then I get this K minus L. And now I can first, so combining everything, we can choose now KL larger than C1T, so that this term will sort of kill off the other term. And so we can choose KL. We choose K such that K minus L is greater than C1T. And then we have that the max V in a L neighborhood, which was what we were interested in the graph of this expectation of X phi n of V n minus XV star, which is the supremum norm squared, is just going to be less than or equal to epsilon E C1T plus 4m C1 cap T K minus L over K minus L factorial. Okay, and now I can just send n to infinity. Then I can choose, if I send K to infinity, then L to infinity, and epsilon down to 0 to get the result. So of course you have to check that everything is okay, but you can do that. And what is the point that I'm using here? I'm using here that of course this is going to decay because I've chosen this C1T over K minus L to be something that's less than 1. And so then if I take a factorial, then I get a good control. Okay, so I don't think the details are so important as to more the style. All you have to do is a coupling using these isomorphisms, and then you also have to use a little bit of the graph structure. Is that clear? That's the main thing. Obviously, all the little estimates are not important. But any questions on this before I move to the second question?
Just a quick question. I guess if we replace the coefficient in the Brownian by, I mean, if we now the coefficient depends also on the structure and the local interaction, so we will have the same, I guess, result.
Absolutely the same argument. I just didn't want to keep writing sigma, because it's the usual Picard, because I'm assuming Lipschitz continuity of sigma as well.
Yeah, so it's enough to assume Lipschitz continuity for the coefficient of the diffusion, for the Brownian motion, right?
Yes, yes.
Okay, thank you.
That we do always throughout B sigma, just even for strong solutions. I mean, you could potentially, relax many of these things, and you'll have to do more careful estimates here. And I'm not sure exactly what relaxation will be allowed. So we just wanted a basic.
Thank you so much.
Okay, thank you. So, so now let's move to question 2, which was the empirical measure convergence. Okay. So now remember that what we're looking at is we have this mu gn xn, which is defined as 1 over gn, summation v in gn of the delta mass at the path of the trajectory of the dynamical system starting with initial condition xn. Okay, so this xn, sorry, it has to be on top. Okay, so now the question is, what did we know about this in the complete graph case? Remember when Gn was the complete graph, we know that this converges to a deterministic limit, and we know that that deterministic limit is equal to the law of a typical particle, right? So we want to ask the same question. So question 2a, does mu Gn xn converge to a deterministic limit mu? Okay, and when I say converge, obviously converge weakly, right? In this space of probability measures on the trajectory. And when it does, maybe there are some cases when it does, maybe it always does, or if it does, let's say, if it does, then does mu coincide? Because now I'm always have this assumption of the underlying assumptions which guarantee this local weak convergence already for us, okay? So I'm asking this question in that under the same assumption. So we have a limiting process, xgx. So now I can ask, is it still the same as the law of the limiting process? Okay, so again, I'm assuming that, of course, Gn is converging to G, the usual way. So I'm assuming that, right? I mean, without that, we will not have, we know arbitrary things has happened. So we're always assuming still that Gn, xn is converging to Gx in G star or G star RD as we go. Okay, So we have the marked graphs of the initial conditions converging in the local sense. And now I want to know whether we have a deterministic limit and whether that deterministic limit is the law of a typical vertex in the limit.
Kavita, now we need to assume local weak convergence? Or just local
I'm just
convergence?
asking this question under that assumption. I'm just having, because we can do that because I'm asking this question under, this is just to get some intuition, right? Then I'll write the theorem. But I'm saying, okay, then because otherwise I cannot phrase this question this way. And these are natural questions to ask, right? So I'm not assuming any local weak convergence or anything. I'm just saying that I have the same assumptions as I did for the other theorem, which is, I have this B Lipschitz, et cetera, et cetera. So therefore, by theorem 1, we know that Gn(xn), if Gn(xn) converges locally weakly, then so do the dynamics. So I can ask this question such that it makes sense. Yes?
Okay. So I'm sorry, because I'm confused about local weak convergence or local convergence.
No, just local convergence.
Just local convergence.
Yeah, I mean, we call it like sort of local convergence in the weak sense because these could be random graphs. So that's why I say local convergence in law,
Okay, thanks.
See what I mean? So, okay, the space of isomorphisms of marked graphs forms a Polish space. So if I consider a random element, I can do weak convergence on that, right? That's what I call local weak convergence. Because then it's random elements and not just local convergence, which is for deterministic.
I see, but the root is uniformly at random on the vertex of the graph.
Yes.
What?
Yes, the root is uniformly at random, as I said yesterday as well. I'm choosing the root uniformly at random on Gn.
Okay.
So all my graphs here are rooted graphs because otherwise I cannot talk about G star. And the root is always chosen uniformly at random from the finite graphs Gn. And for whatever I say today, the Gn's will always be finite. Okay, obviously the G not necessary. We're not assuming that G is transitive. And for now, this question is just being asked when G is deterministic, the limiting graph, because I've said in Gx, not in law. We're later going to ask, of course, for random graphs as well. Okay, but even for random graphs, my question is the empirical measure converging to the law of the process on the, so it's still deterministic. Even if the graph is random, the process is random. So this will be random, the graph is random. Leo, does that answer your question? So even if the limiting graph is random, the law of the process on that graph at a typical vertex is still a deterministic quantity. Okay, great. So how many of you, I don't know if you can raise your hands or something. So do you think that we will have a deterministic limit in general? So Guillermo, you're not allowed because you studied this problem. Okay, Ahmed. Yeah, you think, okay, yeah, okay, so maybe, and is it always deterministic? Will it always be deterministic? So can we try to remember why was it deterministic in the case of a complete graph? It was deterministic because we saw that neighboring vertices were asymptotically independent. And so we could, I'm just reminding you that we thought, okay, we could apply a sort of strong law of large numbers. I mean, it's not exactly strong law of large numbers, but we had asymptotic independence, right? So then a strong law of large numbers suggests that, okay, you have asymptotic independence. So this quantity will go to its expectation of one of the terms, which is simply the law of a typical particle. Yes, everyone remembers that that was the reasoning for the complete graph. But however, for the this sparse graph, we know that neighboring vertices are strongly correlated. They're not going to become asymptotically independent. So how many people still believe that you will get a deterministic limit?
Sorry, do we assume that the neighboring 2 is going to infinity or is the neighboring is fixed? Because this is a question, I guess.
No, I'm doing it in the local weak convergence case, right? So just let's do it, be very, very precise. Just take a random deregular tree, if you want, a graph. So your GN can be a random deregular graph. So
okay, so we still got the deregular.
We're not like, I'm just reminding you what happened in the complete case. Now we're trying to understand what happens in the sparse case.
So yeah, in this case, I don't think so. Yeah.
Okay, so the point that I want to make is it's not obvious what's happening, right? It's not completely obvious a priori because the same argument doesn't work in any case. But you might think that you still have some averaging over, right? So it might be that neighboring particles are not, but maybe you have some averaging. Okay, so that's what I'm going to try to explain. So let me first tell you, I have to introduce some definitions, which if you at least read the exercises today, then that would be useful. But when we do these graphs, so far, remember that when we talk about GN converges to G, in G star, we have to have GN connected, right? Because the G star is only on rooted connected graphs. But we obviously want to talk about convergence of random graphs, which may be disconnected, right? Like Erdős-Renyi with CRM-PIMS, where Pn is maybe less than, log n over n, right? So for instance, in such cases, you want to look at this. So in this case, let's look at this definition. We can easily talk about convergence of any random graph. So consider a finite sequence. I mean, a sequence of finite graphs, sorry, not a finite sequence. Sequence of finite graphs, possibly random and possibly disconnected graphs, Gn, and let G be a random element, G star valued element. Okay. Then we want to talk about a notion of Gn converging to G in law or in probability, again, in the local weak sense, okay? Even though it's a disconnected graph. So we can do that by simply saying that the following. So then Gn is said to converge to G in probability in the local weak sense. So of course, you're going to have something that involves each of the connected components. If I take 1 over the vertex set, and then I sum over every component, I'll tell you what CV is. It's simply the connected component of Gn converging to containing V. Okay. So where CV, for any graph, CV of H is for any graph H, CV is the connected component of H containing V. Okay, is that clear? What the definition, anyone has any questions about the definition? And this here denotes convergence in probability. Remember, the left-hand side is simply a random variable now because f is a continuous bounded function. So this is just some random variable. So it's the usual sense of convergence in probability for random variables. Okay. And now we can also have convergence in law. So I'm not going to rewrite the same thing, the same sequence of finite graphs Gn, and G is a random G star valued element. So maybe before I say that, I would like to say that that you can do the same analogous for marked graph without putting all the details, since it's something that is, I'll just write the final thing that if Gn summation V and Gn f of CV, the marked graph, right, So the connected component of the marked graph is simply the connected component with the marks in it, converges in probability to expectation of f of gy. Okay, this is for the marked graph setting. So now f is, of course, in continuous bounded functions on the marked graph. Is this clear? I'm not writing all the statements previously. Okay, and now this is called convergence in probability. And if you are wondering sort of what does this mean? So this is, as I left as an exercise for you. And that's what I wrote. And I said, you can see that really this is equivalent to saying, let's say this, when I say this is, let's say star. Oh no, let me call this something. Let me call this local convergence. So local convergence in probability. So LCP. So LCP is equivalent to saying that the limit, if I take a graph and I look at all its components, right? So I put a delta mass on all its components. So this is a measure on graphs, right? So because remember that our original convergence only allowed us to understand connected graphs. So we're trying to just extend that. So the natural thing is to say that this converges in probability. So I'll write this like this. So this is a random graph measure. It converges in probability to the law of G. Okay, so it converges. So this is, so in the space of measures on graphs, on equivalence classes of graphs. Okay? So I'll call this exercise LCP. Okay, any questions about this notion of convergence? So all the local convergences that you know, for Eder-Shreni to the Galton-Watson and so on and so forth, satisfy the stronger form of local convergence and probability. The original one that we have, I'm just going to put the definition 3, is just convergence in law. If you do convergence in law, and if you're not following all the details, you just have to remember for understanding that there are two notions of convergence. One is stronger than the other. When you talk about convergence of these graphs, just like usual modes of convergence and probability, right? Anybody has done the first year, always checking about exercises on modes of convergence. So it's the same thing here. So for the same thing, you say that GN converges to G in law if looks very similar, except now you put an expectation because all I want is the law. So I take the law, I take these graphs and I look at V and Gn. I take some function of the components, converges to expectation and FG. So you should just convince yourself, if you're not very familiar, this is an excellent exercise. Okay, so this is an excellent exercise to just say, okay, suppose the graph was connected, then this would just reduce to convergence in distribution on that Polish space and convergence in probability in that Polish space. So there's nothing very hard about this. Okay, it's just that you see what that means, and then you just extend it to cases of disconnected graphs. So our theorem, any questions before? Okay, so there were two notions of convergence. One is convergence in probability and convergence in distribution. And one of the exercises I asked is to try and find something that can converge in distribution, but doesn't converge in probability. And I've already told you that Eder-Shreni, the configuration model, the random regular, everything I showed yesterday converges in probability. So you'll have to find another example, not those, but it's not it's not a hard example, and I might have intended. Okay, so the theorem 2 is that if Gn xn, and here I'm always assuming is converging to, so here now Gn, Xn are random marked graphs, which are not necessarily connected. Okay, so it converges in probability to a random G star X element, Gx, then, and of course, very important, and Gn is going to infinity, then mu Gn Xn converges to the law of Xgn. Okay, is this clear? So it's saying that when you have this convergence in probability, then you have the same result as in the complete graph case. But even though, of course, the proof is not the same and it's not exactly the same reason. Any questions on this? Just to see if you're following, why do I need this assumption? So what are we saying? We're saying there are cases when you do have a deterministic limit, and that deterministic limit will coincide with your original graph, right? That's the basic message. So this is again with oops, sorry about that. Okay, lacquer R. Okay. So anyone wants to tell me, is this necessary, or did I just say it for fun? The Gn goes to infinity. Do we think there could be cases when the random graph, so if you've forgotten what mu Gn Xn is, remember this is 1 over n, 1 over the size of Gn.
Kavita, what
Yeah.
happens if Gn is fixed? I mean, it's the
exactly.
circle.
Yeah, let's just take a cycle of K, 5 cycle, and then just say Gn is the same thing for everything. Then you know that your empirical measure will be stochastic. It'll converge to the same because there's only one graph, but it's just going to be a stochastic.
Yeah.
Right? So therefore, it's not a good, it's obvious that you need, I mean, you know that even in the complete graph setting, right? You take complete graphs, if they're all, the vertex size is not going to infinity, then the empirical measure also is not converging. So you obviously need some, like the strong law of large number, you need some n to go to infinity in order to be there enough mixing and some chance of anything to be deterministic. So I'm just trying to see that this blue condition is not a restrictive condition and it's not a surprise, right? The question is, of course, for graphs that are going to infinity sizes, when do you have this? Okay. And so what are the elements of this proof? Maybe before I state the elements of the proof as to why it holds, let me say what happens in the other case, in case we run out of time. Okay, so now I'm going to say, let's take the C of the root, let's say, the connected component of the root of an Erdős-Rényi NPN. So let's even take a simple one. And C over it. Okay, so now I take this. This was Erdős-Rényi, right, which is converging to, we know, the Galton-Watson. Then we know that so this is the connected component of the root of an Erdős-Srény graph. Is this clear to everybody? Okay. So that's a connected graph. And I claim that the mu of Gn, and you take Xn to be anything, some ID, it really, that's not so important here. So Xn converges, it does converge to something, but it converges to a stochastic limit. And I'm going to see if you have the intuition to try and see what might happen. I mean, we're going to discuss that, and that's going to be sort of the results today. Okay, so anyone with, firstly, if I took the connected component of the Erdős-Srény, or if I took the Erdős-Srény, in terms of local weak convergence, there's no difference, right? Because local weak convergence only talks about the convergence of the connected components. Is this clear to everybody? So if it's not, you should go back and think about it. If you have a disconnected graph, you're talking about convergence, whether you take you're only looking at the connected components, so it's going to be exactly the same. So you might say, okay, then how is the empirical measure different? The empirical measure is different, right? Because now you're averaging over a potentially smaller neighborhood. Yes? So can anybody, if from what they know about Erdős-Srény graphs, tell me one case in which you might expect it to be easy to show that this is a stochastic limit? Anybody? So remember that C rho Gn Cn converges local convergence, so weakly, to a Galton Poisson C graph. So there's nothing that you need to know more than what I've already told you today. That's the hint. Did we have any examples when we knew about a stochastic limit? Well, we said if the limiting graph is finite, then of course the empirical measure will simply be will converge to the empirical measure on that finite graph, right? So note, whenever Gn converges to G and G is finite, so this is local, G is finite, we know that mu Gn of Xn will just converge to mu G of X. This is not hard to see. It's because local weak convergence tells you what's happening in a finite neighborhood. If you end up in a finite setting, then you're going to know, the empirical measure convergence just follows from local weak convergence. Okay? I'm assuming always that we're under this, assumptions that we have our local weak convergence just for simplicity, right? Okay. So do we know any cases when the Galton-Watson with Poisson offspring distribution is going to be finite almost surely?
C.
When we have extinction?
Yeah, so when C is less than 1, right, this limiting graph G Poisson C is finite. So it's obvious that the limit will be stochastic, right? But what happens for C greater than 1? Do I still have a stochastic limit?
Kavita, what do you mean by stochastic limit?
I mean, what do we have? We have a limiting measure.
Yeah.
But the measure can be random, like it is for mu G and Xn, or it can be like the law of something, which is a deterministic measure.
In this case, that depends on the randomness of the graph.
Yeah, so that's our whole question, right? We are all talking about, we have empirical measures that are random measures, right?
Yeah.
So why are they random? Because they are delta masses on something that is random, these random paths, right? all these empirical measures of any random process are delta masses on these random paths, which even if you had no drift would be Brownian motions, right? For instance.
Yeah.
So you have random measures, and we're trying to see if there's enough averaging. When do these actually converge to a deterministic limit, like they do in the complete graph case? Right?
I see.
By deterministic, it's still a measure, of course. It's a deterministic measure and not a random measure. So here it will be a random measure. When the limiting graph is finite, then this measure will also be a random measure.
Because of the randomness of the limit, right?
Yes. In that case, so now I'm asking.
I mean, the graph limit.
Yes. So then the result is that when C is greater than 1, then this converges to the law of the root particle on the event of no extinction. And it converges to mu G X. So G is this Galton-Watson C on extinction, on the event of extinction. So it's still a stochastic limit, even when C is greater than 1. But mu Gn now, on the event where it's extinct, it will converge to the stochastic. And on the event when it is not extinct, it converges to the law of this. And though I stated this result for the case of the Erdős-Renyi, we actually proved this for a very large class of graphs. So this is somewhat involved, the proof of this, which uses like sort of duality and Poisson duality of certain graphs. But under general conditions of certain classes of graphs, we see that the connected components, the empirical measure of the connected component is typically, can be stochastic, and is often stochastic. Okay, so we see that the limit of empirical measures for sparse graphs is more subtle. So as a summary, is more subtle than in the complete graph case, but it can still be characterized for large classes. And so since I'm 5 minutes over, I should stop here probably. But if there are any other, yeah, I should stop and take questions.
So just a minor question. So theorem 3, if I read it correctly, is a relatively straightforward corollary of theorem 2, right? Or is there some?
No, there's a little more work to do. There's quite a bit more work to do, but it does use elements of corollaries. It looks like, oh, all I'm doing is I condition and I see what happens, but there's actually more work to do. You have to first identify the class of graphs, but it does use theorem 2. But there's more work, like use Poisson duality, because when you say when it's conditioned, you have to sort of see what the graph looks like, and so there's a little work to do. And you have to know something about the properties of that graph and its size on extinction and non-extinction. But it uses the elements. The intuition is coming from theorem 2. And the fact that for limits of finite graphs, basically the elements that I actually spelled out. But the proof of actually this theorem is longer than the proof of the first theorem, in the sense of, the first theorem uses many elements. So yeah, if you put it together, that's also quite long. Yeah. First theorem being theorem 2, the global empirical measure. So any questions?
Yeah, can I ask a question?
Yes.
It's not related to the proof, but on the model. So here the dynamics depend at the step k+1 depend on, it's a function of the dynamics step k plus some independent noise on the neighborhood.
Yes, in the Markov chain case, yes.
Yeah. I don't know, is it possible to put some around, like in the common noise?
Yeah, no, we actually thought about this a little bit. I think it's quite more complicated.
Yeah. No, I was thinking about the systemic risk, for instance, application, because maybe there are, and I don't know if I missed the point. How is it important? How much is it important, the assumption on the initial conditions?
Okay, so two things actually. Let me first answer your first question. I actually said that is harder because that is for question 3. Okay, I mean, which
Okay.
I discussed, because we did look at this common noise trying to answer question 3, which is my goal here, to understand the typical dynamics in an autonomous characterization. But for this local weak convergence, I don't think it should be that much of a problem, because you can do the same thing. You can condition on the noise.
Yeah.
On the common noise, everything else is independent of that. Everything will, I don't think that local weak convergence should be fine. And I think the empirical measure will also go through.
Okay.
But this is what I think. I mean, I haven't done it out, but for those two, I don't think, okay. I'll be a bit more careful about the empirical measure convergence, but the local weak convergence will go conditionally, no problem. But maybe that leads me to maybe tell you in two lines to everybody, what are the key elements of the proof of theorem 2, right? So then why would it fail, or why could it fail? So we said that we don't have asymptotic independence with 2 neighboring vertices, right? And then we wonder, how do we still get a deterministic limit when there's still strong correlations? Well, the answer is you're averaging over the entire graph, and convergence, local convergence in probability implies that if you take 2 random vertices, then their distance is going to infinity. Okay, like, so if I take a uniform, so say, just take a graph, and if you have local convergence in probability, and you take 2 uniformly chosen, but 2 independently random vertices there, then their distance will converge in probability to infinity, diverge in probability to infinity. So that's actually an exercise that I will put for you people for the next class. So given that, you can average over the entire graph, so you can show that if there is some correlation decay, then you don't have asymptotic independence of neighboring particles, but you do have decay of correlations of particles that are far away. And that is what helps you get this deterministic limit. And so really the main ingredients for that proof is showing asymptotic independence in this other way, showing that this local convergence in probability is equivalent to some sort of more general asymptotic independence. But then you have to use correlation decay as well. And the point is that once you have common noise, this correlation may be problematic. The question is, do you still have some conditional correlation decay? And maybe that could be made to work.
Yeah, okay. And about the initial conditions? So how is it important, the fact that there is, as far as I understood, there is a uniformly, so you use in a one bound where you prove the, so if you if you relax this assumption, you have to change the techniques, let's say. Or
that's a good question. So there actually, the reason for that is if you assume IID initial conditions, then you can relax that. But I should say actually all our theorems assume that marked graphs converges, right, with initial conditions. So then a natural question, which I didn't address, is for what natural marks, initial conditions, do you have this kind of local convergence? And of course you have it IID marks. That's not hard to show, that if you have graphs which converge, then if you put IID marks, they also converge as marked graphs. But we were interested in also looking at some dependent. For instance, if you put a certain Gibbs measure, then would you still have this convergence? And we proved that in our paper. And for that, to allow dependent, if we wanted to allow dependent conditions, then we needed to put this. We didn't work too hard to remove it though. But it's easy to see where that bound is coming up, and with some randomness assumptions, you may be able to get rid of it.
Okay, thank you a lot.